In much of the world, buildings are responsible for at least 40% of a country's carbon emissions. This makes buildings more important than any other sector when trying to address the climate emergency. So we clearly need to be building low energy, preferably zero energy buildings. And we know this is possible, as there are many such examples across the world. Unfortunately, if we look at the data for the energy use of most new buildings, we know we haven't in general been delivering such buildings at all. In fact, it is common for new buildings to use roughly the same amount of energy per annum as much older ones. At the University of Bath, we believe modelling the energy use and carbon footprint of buildings can help us out of this rather embarrassing position. But it has to be a certain type of modelling, done at a certain moment during the design cycle. In essence, we're talking about modelling for design, not for compliance with building regulations or codes. We would argue that without modelling, or at least making some calculations, you are not designing at all. This is because to design is to design for a purpose, for a function, and given the climate emergency, a clear purpose is lower or zero carbon emissions. So you need to find out as soon as possible whether you stand any chance of matching the client's desire for a low energy or low carbon building. You need to know this as quickly as possible because most of the required changes might include dramatic alterations to the architecture. So you need to model. A connected reason to model is to be able to drill down and see what parts of the design could be changed to reduce the energy use or carbon footprint most efficiently. Hence, you need to be able to rank order the energy use of the major components, walls, roof, windows, infiltration, boilers, etc., to be able to see which ones need urgent improvement and which ones are just minor players. To do this quickly implies the use of computer modelling. Very few architects can do this using the computer tools out there. Such tools are complex, specialist software products, and almost impenetrable if you only use them occasionally. Given that the orientation, glazing ratios, wall construction, shape, and many of the materials get decided very early on, unless we model almost from day one, most of the potential to improve the energy and carbon performance of the building will have been lost. Yes, we might be able to tinker with U values, etc. later on, but this will only have a marginal effect. Much more important will be removing the massive air conditioning load the architect has created from the vast area of glass she drew facing the summer sun. Chances are that no reasonable amount of PV cells are going to be able to make up, and the building will never be able to match the client's desire for a low energy building and the planet's need for one. The energy engineering team are unlikely to be appointed until much of the architecture has been fixed. So it is clear the architect might need to be doing the modelling, not the engineer. And whoever does it, the tools need to be quick to use and designed to be used at an early stage of the design cycle, when the values of many variables are unknown or only approximately known. We clearly need to include the energy used to heat and cool the buildings, plus that used to provide hot water for showers, etc., and electricity for lighting, computers, etc. We call this the operational energy use of the building. We may also need to account for integrated renewables, typically PV cells and solar hot water. So what needs to be modelled to get a good idea of the operational energy use of a building? We first need to model the heat losses or gains through the opaque fabric, i.e. through the walls, roof and ground floor. Then we need to add in the energy balance of the windows. Windows lose heat, but they also gain heat by letting sunlight into the building, so we need to model both of these aspects. It is quite easy when modelling to ignore how the building is heated or cooled and the efficiencies of boilers and the distribution system, so we need to include the building systems, including the hot water distribution system. Conducting elements such as metal wall ties or steel lintels or window frames are termed thermal bridges. These will need to be included in the model, as we might need to design them out if they are responsible for substantial energy losses. We also need to include the movement of air into and out of the building. We normally break this down into infiltration, i.e. uncontrolled ingress through cracks, etc., and ventilation, for example, from the opening of windows. Then we need to include heat from incidental gains, for example, those from artificial lighting or body heat. Given this list of items to include in the operational energy model, the next question is how much detail do we need to provide about each item? The bad news is that you need to include quite a lot of information, and ignoring the even minor bits of the physics leads to large errors. The good news is that many of the variables can be represented by default values. The important thing is to include them, not ignore them. Ignoring them is just really including them, but setting them to 0. Just about any guess you can make will be better than this. Here's an example: hot water use. Think about what happens when you turn a tap to wash your hands. You might use half a litre of hot water, but if the boiler is 15 metres away, and if the pipe 15 millimetres in diameter, a further 2.5 litres would have been heated and left sitting in the pipe run after you turn the tap off. This indicates a possible 5-fold error in the energy estimation. Then maybe the water has come from a hot water tank, which will have its own losses. Finally, the water might have been heated by a boiler, which will not be 100% efficient. In total, this can create a 10-fold error in the estimation of energy used to supply the hot water. Although frequency of hand washing, the length of pipe, the form of the hot water tank and boiler all affect the precise answer, using reasonable default values is going to be a lot better than ignoring these factors completely, i.e. setting them to 0. Unfortunately, many such factors are very frequently ignored, particularly during the early stages of the design cycle, which is just when we can make big changes. For example, heating the water at point of use, or making sure the boiler is close to where the water is used. Another example would be the shading of windows. Often windows are modelled as being right on the outside of the building, not set into the wall, and the surroundings ignored, whereas buildings are most often surrounded by other buildings, trees and hills. In addition, some of the window will be frame, not glass. Taken together, these factors greatly reduce any solar gain, typically by at least 50% and commonly by 75%, completely changing the energy balance of the windows and probably the building. Again, just using some sensible guesses for such factors will greatly improve the accuracy of your model. In fact, we would go further. If you don't include such factors, your modelling will be pointless. Not only is energy used to run a building, a lot of energy will be used to make the construction materials, then assemble them on site, and this will have resulted in carbon being emitted to the atmosphere. We term these the upfront carbon emissions. For a typical building, these carbon emissions will be similar in size to the carbon emissions resultant from many years of operational energy use. However, as a low energy building will hopefully have a very low level of operational energy use, the embodied emissions can start to dominate the whole life carbon footprint of the building. Getting an accurate value for the embodied carbon emissions is difficult, especially during the early design stages, as the detailed structural engineering will not have been completed. So you're unlikely to know, for example, how many tons of concrete might be needed for the foundations. However, benchmark figures do exist, and these need to be included in the modelling so you get some idea how important embodied emissions might be, and whether any building integrated renewables might be able to offset them. Without this knowledge, promising a client that you can deliver a low carbon building might be setting an unrealistic expectation. So what can we conclude? Firstly, given the critical role buildings will play in the climate emergency, we need to be able to deliver low energy buildings. We know some people can deliver such projects. We now need to help everybody deliver them. We believe modelling can really help with this. Being that most of the important energy and carbon decisions are made early in the design cycle, if modelling is to have a major impact, it needs to be done right at the start, and hence by those present at the start, most commonly architects, but also engineers if they have been brought into the project early. This means that any tools need to be quick and easy to use, and hence possibly based on an interface most people already use, such as Excel. Such tools need to cover operational energy use, embodied carbon and renewables, all in the same tool. They also need to be free to encourage their use. Things like systems and their losses need to be included right from the start. After all, you don't want to find out late that the main focus should have been in reducing hot water distribution losses rather than heat loss from the roof. Complex factors such as shading and distribution losses need to be built in and set to sensible default values rather than set to 0, but still adjustable by the designer. With all this in mind, we created Zebra, or the Zero Energy Building Reduced Algorithm, to allow almost anyone to model energy use and carbon footprint of a building on day one. We hope you will find Zebra useful. In the next video, we will look at using Zebra to model a building. Thank you.